So, hi everyone, my name is Diogo. I'm a student at the University of Aveiro and at the Institute of Telecommunications, and I will be presenting the current work that I've been developing titled Multi-Cluster Migration of MEC Applications. So, nowadays, with the increasing need of more scalable and flexible solutions, we have been seeing an increasing adoption of cloud computing. However, it usually faces a problem, which is the distance between where the data is generated and where it is processed, which limits some applications. To address these challenges, edge computing appeared as a solution that enables the positioning of computational resources at the network edge. While in cloud computing, data must traverse the core network and aggregation layers to reach the destination server, in edge computing, computational resources are brought to the network edges, reducing the distance to user equipment and alleviating the load on the core network. MEC, multi-access edge computing, is one of these paradigms that has been standardized by ETSI, which has been pushing its close integration with NFV. In the MEC reference architecture, NFV enables the virtualization of network functions, while MEC complements it by bringing the computing capabilities to the network edge. Recognizing that no single operator can provide universal infrastructure coverage and that multiple MEC systems need to communicate with each other, the current version of the ETSI MEC architecture already includes a MEC federator component. This MEF is expected to be able to manage underlying MEC systems and facilitate coordination with other domains, creating a unified edge computing ecosystem that maximizes resource efficiency. The necessity of these federation capabilities can easily be seen through a practical application. While before the MEC was limited to its own infrastructure, with the integration of federation mechanisms, it can now coordinate with other domains, enabling the sharing of resources. Additional to this, the limitations in MEC federation standards, as current ETSI interfaces do not provide a full solution for a complete federation scenario, and the gaps in MEC application descriptors, as the current definition do not support the division of an application into multiple components, such as it occurs in VNFs, with the lack of practical implementations, further motivated this work. To address these challenges, we defined the federation-aware architecture that extends an existing open-source MEC and FMV platform. This architecture is built on top of 5 goals that guide the implementation. They are to support the integration of federation mechanisms, enable application migration across different domains, provide fine-grained control over MEC application components, adhere to existing standards defined by ETSI and GSMA, and ensure that services remain available during migration. This is the defined architecture. Here, the existing platform in yellow had already made some improvements to the base MEC architecture with the inclusion of a matrix collector agent within the season and the definition of the practical deployment scenario using Kubernetes for the MEC hosts. Also, it uses OSM as the NFV mano to enable orchestration of MEC applications as network services. However, to enable federation and multi-domain orchestration, this was not enough. For that, we now added 2 new components, the MEF and the matrix forwarder. Regarding the MEF, it was designed to provide a service layer that exposes the functionalities of the underlying MEC system through an abstract and standardized API. The MEF interfacing is defined in accordance to the guidelines outlined in GSMA interface APIs, with some adjustments to allow the proposed division of the MEC applications that we will see in a bit. The matrix forwarder enables the sharing of metrics and available resources between domains, allowing them to be aware of the resources the other environments have available and ensuring that each domain receives only the expected data and not data that belongs to other domains. To allow the fine-grained control, the current MEC application descriptor standards had to be improved. considering these adapted descriptors based on the standard ones, while before only a single application could be provided, now each component of the application can be individually defined, can run on different hosts, and have their own migration policy. For this all to be possible, some new features had to be added to OSM. The first was to allow the enabling and disabling of KDUs, both at instantiation and at scaling operations, in order to allow different components of the application to be running on different network services. The second was to allow the selection of the node where the KDU would be installed, in order to ensure that the component would be running on the node with a certain available resources and not be randomly placed. To avoid service downtime, we adopted a make before break approach, meaning that a new instance of the component needs to be ready before the original one starts being terminated. With the additions to the architecture, the system now supports orchestration of MEC applications in both external and internal domains. On the internal domain migration, no federation coordination is needed, and the system can handle the full orchestration internally. For that, we are using the built-in OSM migration feature that allows a running KDU to be moved to a different node within the same cluster. On the external domain scenario, a MEF is needed to act as a coordination point, and now the communication passes through it here. Here, we already used the implemented features, disabling the necessary KDUs on the origin network function and activating them on the other domain. Still, to maintain the make before break approach, the old KDU is only disabled after the MEF notifies that the activation on the partner domain was successful. Passing to the practical analysis, to evaluate the impact of the federation in the migration process, we set up a test environment that allowed the benchmark of both federated and non-federated scenarios. This consisted of one user equipment that could reach both domains and that was responsible to generate traffic for the running application. For the non-federated scenario, only a single domain was involved, with the application migrating between two nodes of the same domain. For the federated scenario, both domains were involved, and the migrated application moved from a node in the first host to another in the second domain. While both domains had the same stages, they occurred in different orders. This was due to the nature of UDP traffic and how it is handled by contract in the Linux kernel, which keeps the state of network connections if they are considered active. This impacted our non-federated scenarios since we use the built-in migration operation from OSM, which basically updates a running Helm chart. And as we are using the same IP to keep the connection, it results that only after the old instance is removed, the new one starts receiving traffic. Due to that difference, we have two important measurements, which are the instance switch, which is the time between the start of the migration until the first request is received by the new instance, and the total time, which also includes the time to disable the old instance and release the old resources. Both scenarios were tested 100 times, and the most eye-catching results are clearly the considerably higher instantiation and total times from the federated scenario. The biggest difference arises from the instantiation time, in which, while in the non-federated took only about 6 seconds, on the federated one it goes up to 36. This is a considerable difference. However, after an analysis, we concluded that this increase was mainly attributed to the operational characteristics of OSM. In the implemented federated scenario, migration involves the creation of a completely new network service by OSM in our implementation, and this entails additional orchestration overhead compared to the simple updating of the Helm resource. Furthermore, the instantiation time recorded in the results corresponds to the point when OSM reports that the instantiation was completed, And as OSM performs local storage operation and database synchronizations prior to reporting this completion, additional delay was also introduced. Another important observation is the difference in the instance switch time between the two scenarios. While the non-federated scenario had to wait until the old pod was terminated before being able to switch the instance, on the federated one, as soon as the instance was ready, it started being used, resulting in a slightly lower time. Now I will just show a quick demo. In this demo, we'll just do a quick workflow of creating a federation, uploading a MEC application, instantiating it, and migrating. So let's see here in the partner domain. This is our platform. We can create a federation. This federation assumes that the trust, security, and policy related agreements between the operators are pre-established. So here I'm just going to introduce each other credentials to authorize the federation. So first I'm going to introduce the partner, which are saved here. And then I'm going to do the opposite, and on the partner also create a federation with the origin. Okay. Now that we have the federation, I'm going to upload a MEC application. This application will have two components just to showcase a bit of the granularity added to the application descriptors. Oh, I already have it. Okay, let's just test. The config parameters that we are using are exactly the same as OSM. Let's check. So both applications are already running, and in the OSM, you can see that it created a network service. Should be right. Now I will just start the migration. I will start it manually, but it is supposed to be automatically detected when a service level agreement cannot be fulfilled. And once it's detected, it starts migrating. Let me just go grab the application ID. And so I'm going to migrate from this application the component MEC test server. This cluster. So the application is already detecting as migrating. And here it is, also migrating. Currently it is on domain partner. a bit, okay. This is what we told about the orchestration time that it takes when migrating. Okay, and now the migration occurred with success, and it is now running in domain IT Aveiro and at the node that we specified. Then, after that, only after that, the old instance starts being terminated. Okay. So, to conclude, this work presented a solution for enhancing the MEC platform with federation capabilities. The proposed architecture successfully allowed for the management and coordination of resources across multiple MEC systems, and the system proved effective in handling application migrations across distinct domains. For future work, we expect to integrate the MEC system with a 5G core for network-aware migration decisions. We want to explore service communication, security, and charging aspects in federated MEC environments. And we want to do, of course, further experimentation. That's it. Thanks, everyone. And if you have any questions, I will just leave here the repositories if anyone wants to visit.